titled this this video "The Myth of Mechanical Advantage and 3-to-1 ratio broadheads." This is a really common trope amongst usually the heavier arrow enthusiasts, talking about 3-to-1 ratio broadheads and mechanical advantage and that kind of thing. And this was a recently published article on broadhead mechanical advantage, in which Dr. Ed Ashby is quoted as saying, "Broadhead mechanical advantage has a more pronounced influence on the outcome penetration of a perfectly flying, structurally secure arrow than any other factor except for FOC." So it's good to kind of go through this and point out the errors that are made in this analysis, and the whole idea of mechanical advantage, and how mechanical advantage is a perfectly good physics concept, but it's been misapplied in this particular case. So let's kind of go through this article and just point out some of the things. Broadhead mechanical advantage, commonly referred to as MA, the ratio of the force that performs the useful work to the force that is applied. When looking at a broadhead, this essentially boils down to how steep the blade angle is, and thus how effectively the arrow's force can be utilized to do the work of penetrating. To better visualize this, first let's break down the terms that will be used moving forward. Okay, so at this point there's not anything particularly wrong, but it's not so much in the basic definitions, but in their applications where there are issues. So let's look at the terms that are defined in this article. Length is the measured distance of the cutting edge from tip to tail. Height, the measured distance from the center line to the furthest part of the cutting edge. So basically, this is half of your cut width. So half of the width of the broadhead. Mechanical advantage, length divided by height. This is the mechanical advantage in the case of a ramp. So that's technically true. We will see where it's not applicable in this particular example, but this is a true statement. Applied force, the amount of force the arrow carries at a specific point of time. And this is one of my pet peeves, and this is one that the Ashby Foundation, proponents of Ashby's work, and Ashby himself gets wrong all the time. Force is not something that is carried by a body. You don't have force, I don't have force, an arrow doesn't have force, a bow doesn't have force, nothing has force. Force is a description of the interaction strength between two interacting systems. So an arrow does not have a certain amount of force. When an arrow hits something, there is a force exerted between the arrow and the object that it hits. But the arrow doesn't have force, and this is something that is a major problem in the physics analysis that Ashby does on much of his work. Work, the required force over a set distance. All right, this is not quite true either. The equation is right, but the interpretation or the way it's stated here is not correct. Work is force times distance, yes. But the distance that's a unit of length. The distance is not just any random distance, it's a displacement, i.e. something moves against a force. And that's going to be super important for us as we start to understand why mechanical advantage is not the right thing to use in this particular example. So we would say that the work that a force does is equal to the magnitude of that force times the displacement of the body that the force is acting against. So the distance that the body is moved that the force is acting against. And then technically there is a cosine of theta. If the force and the displacement are not in the same direction, then you have to pay attention to the angle between the way the object is moving and the way the force is being applied to it. Okay, so let's look at his examples of mechanical advantage. So imagine that you are trying to load a 100-pound box into your truck that is 3 feet high. From a simple viewpoint, there's a 300-pound foot of work that need to be done, but the amount of applied force depends on how we raise the box. Okay, so basically what he's pointing out here is that you are trying to lift this box up into the back of your truck. You can imagine multiple different ways of doing this. You could pull it straight up. You could slide it up sort of a steep ramp, or you could slide it up a shallow ramp. The amount of work that you do in all three cases must be the same. And the reason is because you are working against gravity, and the force of gravity and the displacement, the work that gravity is doing in trying to keep the box on the ground is a fixed amount. Whatever, in this case, a 100-pound box times 3 feet of height, that's 300 foot-pounds of work. That the force of gravity does as you lift the box up in this direction. Now, so in order for you to move the box, you have to be able to counter that work. The way this actually works is that the work net, the total work done on the box, is going to be equal to the work of gravity. That this is the work that is actually trying to pull the box down, plus the work that you are doing. So I'm going to call this the work of the ramp for this particular argument. So these two things, and this is actually going to be 0. So the net work done as you move the box from here to here is actually 0. You can learn this from something called the kinetic energy work theorem, or the work energy theorem. And basically, the net work done on an object is equal to its change in kinetic energy. Well, if the box isn't moving when it's on the ground, and if the box isn't moving when it's on your truck, then the net work done on the box is 0. You haven't changed its kinetic energy any, and so the net work done on it is 0. That doesn't mean that there's no work done. It just means that the work is equal and opposite. The work that gravity attempts to do is to pull the box down. The work that you do with the ramp is to push the box up. So this is going to be equal to the force of gravity times the height. So we'll just put it as times the height. And this is going to be equal to the force that you applied, the applied force, times the length of the ramp, which we'll just call L. And these two things are equal and opposite to each other. So they have the same magnitude, but different signs. In fact, the force of gravity, since it's pointed down, ends up with a negative sign here. Or if you want to do this with vectors, there's a cosine of theta, and theta is 180 degrees, so there ends up being a negative one in there. That's technical. I'm not too worried about it. The basic idea here is that this analysis is essentially correct. What's really happening here is that as you go to this ramp, you are exchanging, if the definition of work is equal to a force acting on a system and displacing it by a certain length L, what you're doing for the same amount of work of moving the box up into the back of the truck, you are exchanging force for length. So here, this is the shortest possible distance and requires the greatest amount of force. And as the angle gets steeper and steeper, you have a longer and longer length, and therefore you need less and less force to move the box up. And so essentially this is exactly what is calculated here. And as we scroll down, we can see that in all cases, the first case you actually have to apply 100 pounds of force. Here you have to apply 50 pounds of force, and here you have to apply 25 pounds of force. But here you only have to move the box 3 feet. Here you have to move it 6 feet, and here you have to move it 12. You accomplish the exact same amount of work in all three cases, but you have to use less force in option 3 with the long ramp as opposed to the amount of force required in option 1. All right, so that's all true, and that is essentially what mechanical advantage of a ramp does. It decreases the force necessary to move the box by increasing the distance that you have to do the motion through. All right, so let's see how he applies this to an arrow. Okay, so now when thinking about penetration, we do not have a predetermined amount of work that must be accomplished. That's actually somewhat true. It does take different amounts of work to do different penetration work. He goes into some ideas here about broadside versus hitting ribs or hitting heavier bone. And all these different kinds of things can result in different amounts of work, and all that is absolutely true. But now let's get to where some things are problematic. Our bows are essentially a simple machine, and however you set it up, we essentially consider its force as fixed. Okay, again, we are making the mistake of assuming that the arrow has a fixed amount of force, and this is simply not true. He's saying it will decrease throughout the flight, i.e., the arrow starts with a certain amount of force, and as it flies through the air, it loses some of that force. And then as it penetrates the animal, it loses some more force. And basically, what he points out is that by increasing the mechanical advantage of the broadhead, then you can get more work out of this fixed amount of force. This is completely wrong. This is almost completely the opposite case here. The arrow does not have force. What it does have is a certain amount of energy, and energy is the capacity to do work. So what we know from the work energy theorem that the arrow has a potential to change its kinetic energy, and whatever the change in the kinetic energy is going to be equal to the work done by the arrow. Okay, that's called the work energy theorem, excuse me. And it's that the changing kinetic energy of a moving body is equal to the work done on the moving body. So this is a fundamental result of physics. And so when you fire an arrow out of a bow, for a given bow, regardless of what arrow you choose, you are essentially going to be firing it with the same amount of kinetic energy. You can look this up, you can do some experiments yourself, but as you change the mass of an arrow or any of its other parameters, you really only change its kinetic energy by a few percent. So the kinetic energy can be considered to be fixed, which means that the work your arrow can do is fixed. There's only a certain amount of work you can do, and that's all there is. That's all that the arrow is capable of doing, fired from that particular bow. So work then is force times displacement. And so what we really want to do to maximize displacement, to make the displacement as large as possible, i.e. the displacement in this case would be penetration, the depth of penetration. We want to minimize the force. So to keep the same W, if you make D bigger, the only way you can do that is by making F smaller. Because whatever we multiply these two together, we have to get this W, and that's the maximum amount of work that we can do. So what we want to do is decrease the force by as much as possible for penetration. And if we make our penetration force as small as possible, then in principle that should increase the penetration depth. So this idea of the arrow having fixed force and we vary the amount of work by changing the blade angle is just completely wrong. The arrow can complete a certain amount of work, and we vary the depth of penetration by changing the forces acting on the arrow as it penetrates. Nevertheless, even though this idea is wrong, still you could argue that his basic concept is right, that if we increase the mechanical advantage of the broadhead as he defines it, then that would result in an increase in penetration by decreasing the force, i.e. a thin, a sort of 3-to-1 blade will experience less force as it penetrates an animal than a shallow blade like this, and therefore you should get more penetration for the same amount of work or the same amount of energy that you have in your arrow. Here's the problem. It's not force times length, it's force times displacement. So let's switch over to a different video to the camera, and we'll look at some broadheads and see exactly what it is that I'm talking about. All right, I've got two broadheads here that I want to look at that fall on sort of opposite sides of the mechanical advantage, so-called mechanical advantage spectrum. Here, the first one is a very classic 3-to-1 meathead. Sorry, I don't know that that's going to focus very well. A meathead broadhead by Toughhead. It's got some foam on it. I need to clean this broadhead up, but it's okay. And this is the classic high quote mechanical advantage broadhead that proponents of Ashby's work would say has a high mechanical advantage and is thus a better broadhead to use than something like this next broadhead, which is a much sort of the opposite end of the spectrum. So this is a iron wheel wide cut. And clearly, if we were to calculate the mechanical advantage of these two broadheads in the Ashby tradition, we would get very, very different numbers. So here's where the big issue comes from the way Ashby talks about mechanical advantage. In the ramp case, as well as in the as talking about the broadhead, Ashby describes mechanical advantage as being essentially the length here divided by the length here. So 3 to 1, that value would be 3. This is something obviously much less than 3 to 1 here. And the basic idea is that decrease in, quote, mechanical advantage will result in this being a more poorly performing broadhead than the tough head. What's completely incorrect about this is the fact that nothing is actually displaced along that ramp. I.e., when this broadhead hits an animal and it hits here, it starts penetrating the tissue right at my fingertip. What happens to that tissue? Does that tissue move up the ramp and end up here? I.e., does the wound channel open this way as the arrow enters? And the answer is, of course, not. What actually happens is as it hits, the wound channel opens this way. Okay, it opens this way. It doesn't slide up, it slides this way. I.e., the true mechanical advantage of this broadhead is not the length of this ramp or the length of the broadhead divided by the width or half of the width of the broadhead. It's the length of this broadhead divided by the thickness of the broadhead. When this hits material, the material is not displaced along the edge here. The material is pushed aside here, and it only displaces a few bare millimeters, and that's the only displacement that happens. So the work equals F times D. The D portion is not this length. The D portion is the thickness of this broadhead. Now, take a moment and try to calculate the mechanical advantage of this broadhead now when we are looking at it in the appropriate way, i.e., this is wedging things apart this way as opposed to this way. And I assure you that is much, much smaller than, or excuse me, larger than a 3 to 1 ratio. In fact, all of your two-blade broadheads are going to have very high mechanical advantages because the displacement is along the thickness of the broadhead, not the width of the broadhead. So what's going on here? Well, let's draw some more and see if we can explain this in a little bit better detail. All right, so let's go back to this idea. So if we have a ramp, and we have the height of the ramp times the length of the ramp, the mechanical advantage of this ramp is indeed the length divided by the height. But what is actually happening on the ramp? On the ramp, we put some kind of heavy box and we displace that up the ramp by applying a force and pushing that box up the ramp. Notice it starts here, it ends here. What happens when we have a broadhead? So I'm going to draw just a really simple, ugly looking broadhead. But what happens to the tissue material? This tissue material here, as it hits, it doesn't go riding up the broadhead. It runs right past the broadhead as the broadhead splits the tissue material. So we're not talking about the same kind of thing. We just don't have the same displacement. The displacement here is this length. This length, there's nothing displaced along it. In fact, what you do is you look at it from the other angle, which is the thickness of the broadhead this way, very, very thin. We might have some kind of ferrule here or something like that. So this is our very, very thin broadhead. But the material hits and it displaces up here and it displaces up here. So the length of displacement is actually this length right here. And that's it. So yes, there is mechanical advantage is very important for a broadhead, but it's the reason that we use thin blades. It's not the width of the blade relative to its length that matters. It's the thickness of the blade relative to its length that matters. And practically all two-blade broadheads and even other kinds of broadheads will generally have a very thin broadhead for exactly this reason, because that's good mechanical advantage. So the question is, what's going on then? Because clearly, hunters, the experience of hunters has been that for many, long broadheads have worked really well. And certainly Ashby does have some data to show this. He does show this in some data in the Cape Buffalo studies that he's produced and has shown data for. Here's what my argument would be. You make a cut. So here's the cut, and let's say that this is the cut that occurs in the animal, and let's say that this, just to make life easier, is a 1-inch wide cut. So we have a 1-inch wide cut here. Now, what kind of broadheads do we have? We have something like a 3-to-1 broadhead that is essentially 1-inch wide that can make this cut, or we have some kind of shorter, stubbier broadhead, something more like an iron will, also roughly 1-inch wide to make the same thickness cut. So to me, this is really simple. It doesn't have anything to do with mechanical advantage. It just has to do with the length of the cutting edge required to make the same width cut. This is essentially the same reason why if I'm cutting potatoes into French fries, I reach for a 10-inch chef's knife as opposed to a 3-inch paring knife. There's just more blade, and it's easier to make the same length cut with more blade than it is with less blade. When I say easier, essentially what's happening is that you are degrading the blade much less when there's a lot more of it for the same 1-inch cut than you are when there's a lot less. So what really is happening is you have two options. You can use a baser steel, stainless steel or some other steel that's not quite as good, where the edges may roll, you may get worse dulling, you may get chipping or chatter or that kind of stuff. But if you have a lot of blade, then there's going to be less damage per inch of blade to make this 1-inch cut here than if you use a short stubby blade. So on the other hand, the other way you could look at things is, well, I'm going to use a super steel. I'm going to use a really good steel that, even though less edge is making the same width cut, the steel that I'm going to use is going to be so good that it's not going to roll, it's not going to chip, it's not going to chatter, it's not going to dull in making that cut. And so there's no harm. And I think this is carried out in testing. So a lot of the more premium, more expensive blades on the market now are made specifically for edge retention, which really counters the need for this 3-to-1 edge. Whereas if you were looking at something like a grizzly broadhead, which Ashby did much of his studying with, the steel in that broadhead is just not very good. And so it will tend to dull much easier than some of the super steels in modern broadheads, and it benefits from having a lot more edge to make the same width cut. And that's really what's happening with this 3-to-1 ratio. You are going to get not significantly greater force working with a smaller blade, assuming the blade stays sharp. And I think this is something that Bill at Iron Will has actually produced results on, where he's looked at push force testing on some of the 3-to-1 long sort of 3-to-1 traditional blades versus his Iron Wills, and found that the push force testing is basically no different between these two. Very little difference for these two kinds of broadheads. And the reason being, again, because this idea of mechanical advantage simply isn't true. You don't have a change in the force because of mechanical advantage, because when we turn both of these on their edges, the thickness of these two blades are about the same. And that's really where the wedging force comes from. It comes from the thickness of the blade, not the edge of the blade. There's no wedging force acting this way. The wedging force is acting along the thickness of the blade, not along its length. And so if you're going to work with a broadhead that has really good steel and is very sharp and retains that edge, it's not really super necessary for it to be 3-to-1, 2-to-1, 2.5-to-1, some really long thing. In fact, you get some advantages by going to the smaller broadhead. They're easier to tune, particularly at high velocity. So for compound bows, there's simply less surface area here, which means that they're going to be easier to steer without having to go to extreme FOC. There's less edge, so they can be easier to sharpen. Really, that kind of that's personal. I don't find broadheads to be difficult to sharpen personally, so that's not a big deal to me. But there are advantages to this smaller broadhead, mostly in terms of arrow flight. So particularly for compound shooters, where high velocity, you're going to have much more planing and other kinds of issues with big broadheads like this than with smaller broadheads. This is a good idea. But it comes at the cost of needing to use a really nice steel that retains its edge, because you're getting a lot less edge to make the same width of a cut. Now, once you go beyond 2 blades or 2 blades with bleeders, then we start to see some differences. So let me see if I can find some other things to look at here. So let's look at for example, this broadhead. So here's a standard chisel tip 4-blade. Once again, once we get back to the blade here, it's really the thickness of this blade that is the mechanical advantage. So this is a very thin blade, so any tissue that hits this blade, it only displaces up and down the edge of the blade a very small amount. And then and essentially that accounts for the mechanical advantage of the blade. However, look at this chisel tip. Notice here that what we essentially have is a surface, a wedging surface, and no matter which direction that the tissue tries to take, it's always going to be displaced by a pretty significant width. It has to be displaced from this point out to the full thickness of this chisel tip. And so that means that you are actually going to be pushing some material when this hits is going to get pushed up here. And that height that you get pushed through, because this is much thicker, that's a displacement. So if you're going to use a chisel tip, a longer chisel tip like this is going to have a much better mechanical advantage than if we had a chisel tip that was sort of stubbier like this. If we had a chisel tip that was stubbier like this, then your mechanical advantage would be very poor. And of course, if we just put a blunt on here, then we would have terrible mechanical advantage, and that would generate a huge amount of push force as this thing impacts animal material. So yes, mechanical advantage does matter in broadheads. It's just not in the way that the Ashby reports describe it. And it's certainly not something where if you are shooting an iron will versus a 3-to-1 broadhead that you are sacrificing any kind of performance because of the difference in, quote, mechanical advantage for those 2 broadheads.